So I'd like to emphasize again that when you have other analytical techniques such as gravimetric analysis, it is quite easy to determine when a reaction has ceased. For gravimetric analysis, that's when precipitates do not crash out of solution anymore. But for volumetric analysis, such as titration, it's actually hard to see whether naked eye where the equivalence point is. What point does the reaction stop? Meaning, at what point does the base fully consume the acid, or vice versa. But nonetheless, there's actually two ways available to determine where the equivalence point is. Well, first of all, you need to know if you have a strong acid being reacted with a strong base, weak acid being reacted with a strong base, or a weak base being reacted with a strong acid. And then from there, you can estimate, okay, the pH of the equivalence point should be at around this value. And you can either see those pH changes with a pH meter. So it's basically a probe which you stick in the solution, in the analyte solution, while you're titrating. Let's say, for example, for this graph, if you're titrating sodium hydroxide into hydrochloric acid. So what the pH meter does is it actually measures what the pH is as you add the sodium hydroxide, again, at least for this graph. And from there, you can actually see, or you can actually plot the curve like this. Okay, there are softwares such as Logger Pro, which do this automatically for you. I think some of our majors are using Logger Pro in the lab, or have used Logger Pro in the lab. But after that, to pinpoint the equivalence point, what you do for this graph is just to write straight lines at those parts of the curve, okay, wherein basically you have flat lines, okay, and then draw this vertical line tangent as much as possible to this steep change in pH. That's where your equivalence point lies anyway, okay. And then from there, you can determine by determining what the values of x and y are, what the pH and what the volume at the equivalence point is. But the most common way, in the absence of a pH meter, is using an acid-base indicator. So an acid-base indicator just basically changes pH an acid-base indicator changes color in whatever pH of the aqueous solution they're in. Okay, now that point at which the indicator changes in color given changes in pH is called the endpoint. Okay, and to pick a good indicator for an acid-base titration, it's actually important to make sure that that endpoint is very close to the equivalence point. All right, so once again, the endpoint is not equal to the equivalence point, but rather, if you want to do a more accurate, more precise measurement, you want it as close as possible. So how do these indicators actually change color when they are at different pH conditions? So first of all, these indicators are complex organic molecules, or simply complex molecules. They're also weak acids, by the way. In fact, they have really, really low Ka values. Okay, and basically, their protonated form, let's say for example here, phenolphthalein, exhibits one color at a certain pH range. People normally call it acidic range, just because the phenolphthalein, or the indicator in general, is protonated. And then once you deprotonate the indicator, which is this form, okay, it has a different color. Okay, so it has different colors whether the proton is with the molecular structure of the indicator or not. Okay, and again, we want that change to happen, that endpoint to actually happen at around the equivalence point. Okay, for phenolphthalein, which most of you actually use or have used in titrating strong acids with strong bases, that change actually happens at pH 9. Okay, but let's look at when you can actually see these indicators. So like I said, an indicator is also a weak acid. So therefore, you can write an equilibrium expression for a protonated indicator in the presence of water. And you can solve for a Ka value. Okay. The presence of an indicator in solution does not at all affect the titration. I mean, it's a weak acid. Some of you might ask, well, what if I'm titrating an acid? Won't that throw off my results? Or what if I'm titrating a base? Won't that neutralize some of my base? So again, remember that these indicators have very low Ka values. Okay, they're weakly acidic, really weakly acidic. And as a result of that, they should at all not affect your results or experiment. At least if they do, it's very, very negligible. Okay, now when you are titrating an indicator, okay, you usually only use around 3 to 5 drops. That's the safe number. And usually the color change is okay anyway. Some people actually say 1 to 3 drops, but whatever. Okay, now if you have an acid analyte, then you will see the color of the indicator change when the ratio of the deprotonated indicator to protonated indicator is 1:10. And when you're titrating a base analyte, you see the color of the deprotonated indicator when the ratio of deprotonated to protonated indicator is 10:1. The useful pH range of any indicator is at pH is equal to pKa plus or minus 1, which is basically just the buffer capacity of the indicator. Meaning, let's say, for example, if you know what the pKa is of an indicator, add or subtract 1 from it. If the equivalence point that you want to work on or want to pinpoint is around that range, then you can use that indicator. Okay, let's repeat that again. So again, from the pKa of the indicator, add or subtract 1 to it. That's the pH range basically at which the indicator should be able to do a good darn job at telling you where the equivalence point is close at. Okay, and you must pick an indicator in which the equivalence point falls within this range. All right. So these are some common indicators. Again, the most common one that you probably have seen is phenolphthalein. So this is phenolphthalein. Okay. So you can see again it changes colors at around pH 9, and the useful range for phenolphthalein is around 8 to 10. Now there are some indicators which you can only use, for example, for reactions in which you really have to work with an acidic medium. Let's say, for example, crystal violet, that's useful for a pH of 0 to 2. So in other words, you cannot, I repeat, you cannot use crystal violet when titrating strong acids and strong bases because the equivalence point is at 7. At the same time, if you're titrating a weak base with a strong acid in which the equivalence point should occur at acidic pH, you cannot use phenolphthalein. It's a bad idea probably, and you cannot also use alizarin yellow, okay, because that only works, or the indicator range there is around 10 to 12. Okay, but again, these values are all just pH is equal to pKa plus or minus 1. All of these, I guess, color ranges per pH. Now, okay, how do we pick an indicator then? Let's consider two cases. So let's say, for example, if you are titrating uh, sodium hydroxide into hydrochloric acid. At what point do you want the indicator to exactly change in color? Okay, so let's look at some values first. Okay, so as we can see here, let's say for example this experiment was done with a pH meter, okay, and an indicator. So this equivalence point is around 6.00 ml, and the pH is around 6.98, very close to 7. Okay, let's look at the other data points. This is around half a drop away from it. This is 5.95 ml. Okay, and the pH here is actually 5.48. Okay, notice that is actually very far from 6.98, a unit of 1.5. Let's rewrite that. So this is again 5.95, and then the pH is at around 5.48. Okay, again, notice the difference between the pHs of these two volumes. Okay, and then next, let's look at this point as well. This one is around one full drop lower than 5.95. This is 5.85 ml, and the pH is actually at around 3.52. Okay, and then finally I want to look at this line, which is the pH here is around 9.07, and this is just a quarter of a drop away even. So this is 6.02 ml, and then 9.07 is the pH. Okay, so again the question is this: how important is it that their indicator changes color at exactly a pH of 7? What I wanted to impress in you in writing these numbers is that notice that as you go from 5.85 to 5.95, we define air coat 1 drop as around 0.1 ml. Okay, notice that as you go actually that far, as you go I guess not that far, but like as you add just 1 drop, the pH actually drastically changes, which is a characteristic of strong acids and strong bases being titrated with each other anyway. And then when you add half a drop, you have reached the equivalence point. Notice how the pH still shoots up. And then when you add a quarter of a drop, so from 6.0 to 6.02, the pH is at 9.07. In other words, it's actually hard to do titrations, especially to control them. That's why there's that meme from the beginning of this titration subsection, as well as in the title page of this chapter slides. So what I'm trying to say here is, if you do calculations, let's say for example at 6.02, in which the pH is actually 9.07, that's actually a good estimate for 6.0. I mean, even 5.95 or even 5.85 should be good estimates. I'll go with 5.95 instead of 5.85, but you get the point. And let's see at 2 possible indicator candidates. So if that's the equivalence point, we have phenolphthalein, which again changes color at pH 9. Okay, and we have methyl red, which changes color at around pH 5.5. Okay, so we can actually here use phenolphthalein as a good estimate. Okay, since again note how close these volumes are. The pHs are so far from each other, but the volumes are so close, so that your choice of indicators is actually wider. Okay, and then let's look at another example. What if we are titrating sodium hydroxide with this time acetic acid? So let's look at where the equivalence point is first. Okay, and then let's look at some data points. So if that's the equivalence point, let's say this point in the graph is actually 12.72 ml. Okay, and that is 9.24 in pH. Okay, this is 12.79. Okay, around 3/4 of a drop. Okay, ml, and that's around 9.95. Okay, And then other interesting points in the graph. Let's look at 12.65 ml, which is this one. Okay, that's almost a drop and a half, or not even. That's actually 3/4 of a drop. This is 12.65 ml, and the pH is actually 7.01. Okay, and then I actually have numbers for this and this as well, but as you can see, they're really close in terms of pH. Well, we can just write them, sure. This is 12.50 ml, 6.41, and then this one is 12.82, a full drop away, and the pH is 10.31. Okay. Notice that this region at which the pH changes is actually less steep than the one from earlier. Okay, so if you were to consider what indicator you should pick, I think let's go back to the first one, by the way. So for here, I forgot to mention, but you can use methyl red as well here. Okay, so you can use phenolphthalein, but you can also use methyl red. Methyl red changes pH at around 5.50. Okay, and again, we have said earlier that 5.95 is a good estimate of 6. Okay, now is that true for this titration curve? So if we consider again these indicators, we note that methyl red is actually not a suitable indicator for this titration anymore. Okay, so you can see methyl red is far this time from the equivalence point. Again, methyl red changes pH at around 5.5 or around 5 even. Okay, but for this one, if you add 5 to, well, if you add 1 to 5 rather, you will get 6, and that's not very close to this value. Okay, so for here you have limited choices. You can work with phenolphthalein and basically an indicator which has a color change, a pKa at around that value. Alright, so let's answer just a few exercises on indicators. We're given here equivalence points, and you're just asked what do you think will be a good indicator for the following titration equivalence points. You're not actually mentioned, or you're not given whether the titration is a strong or weak strong titration, but instead you're just given the equivalence points. Okay, so at the pH of 7, let's look what pKa's are close to that value. So we have para-nitrophenol, okay, so that's 7.2, and phenol red. So it's actually good indicators for pH 7. Again, earlier we said phenolphthalein because we actually know that it's a strong acid, strong base reaction. But here we have no idea if it's strong or weak strong. Okay, so this is para-nitrophenol and also phenol red. Okay, and then the next thing, let us consider pH of 8.79. So around 8.79, that will be, well, plus or minus 1. So that's around 7.79 to 9.79. So we can actually use thymol blue. Okay, thymol blue has a pKa of 8.89. And we can use phenolphthalein as well. Okay, so this one should be thymol blue and phenolphthalein. Okay, and then next we choose for 4.82. The pKa's closest to 4.82 will be we have bromocresol green, okay, and also methyl red. So those are good indicators for that. Bromocresol green and methyl red. Okay, and then for the next one we have 5.28. So for 5.28, let's look again at the pKa values. So 5.28, we have, well, we can actually use the same things too. So bromocresol green and around methyl red. Okay, those are close to 5.28. So let's just put this in quotes like that, just to denote that we're gonna use the same thing. Okay, and then we have lastly 3.27. So for pH 3.27 or equivalence point of 3.27, then we have to consider here methyl yellow. Okay, methyl yellow. We also can use methyl orange. Okay, and we can also use bromophenol blue. Okay, so this is methyl yellow, methyl orange, and bromophenol blue.